Hi all, welcome to the lecture series on Aerospace Propulsion. I am Mr. Manideep Gupta, Assistant Professor from Department of Aeronautical Engineering, MLR Institute of Technology. Today, the topic which we are going to discuss is eccentricity, inclination, polar and sun-synchronous orbits. So, coming to the overview of today's presentation, we are going to discuss what is eccentricity of an orbit and how do we calculate this eccentricity and what is the effect of this eccentricity on a particular orbit. Next, what is the inclination of an orbit? How do we calculate inclination? The definition of inclination. And next, the topic is polar orbit. So, what is polar orbit and what are the applications of polar orbit and how we use polar orbits. The next topic is sun-synchronous orbit. So, what is sun-synchronous orbit? What are the characteristics of sun-synchronous orbit? And what are the applications of sun-synchronous orbit. So, today this is the overview of today's presentation. So, let us start the first topic. So, first topic is eccentricity. What is eccentricity generally? So, we might have gone through this eccentricity in school days. So many people might have gone through this. So, eccentricity is nothing but a deviation from the circular orbit. Eccentricity is a deviation or departure from a circular orbit. So, suppose if I take a circular orbit like this, so if any closed curve deviated from the circular orbit, so whatever the level of deviation, that is given by the eccentricity. Okay. So, in order to have a proper definition, how do you calculate the eccentricity? So, coming to the eccentricity, it is the ratio of the distance between the foci and the length of the major axis of a ellipse. So, eccentricity for a ellipse. So, here if you take an ellipse, then the eccentricity can be calculated with this. So, here the ratio of the distance between the foci. So, if you see the ellipse once, so here you can see this is a ellipse and here this is one foci F1 and this is another foci F2. Okay, and this is a body. This is a body which is moving in elliptical orbit, let us say like this. So, according to the definition, how do we calculate? So, he is saying the ratio of the distance between the foci. So, this is focus 1 and this is focus 2 and the distance between this focus is this one. This is the distance between the focus and we are considering this distance between the focus as LC. So, LC is what? LC is the distance between the foci. And next, to the length of the major axis of the ellipse. So, if you take the major axis, this is the major axis. So, A is the major axis of the ellipse. So, according to the definition, it is a ratio of the distance between the two foci, that is LC, and the major axis, semi-major axis. This is actually semi-major axis and this, so into 2 will give you the major axis. So, LC divided by 2A is nothing but called eccentricity. LC by 2A is called eccentricity. So, if you go to the eccentricity, for a circular orbit, this eccentricity is, for a circular orbit, this eccentricity is 0. Why it is 0? So, according to the definition, what is eccentricity? Eccentricity is equal to LC by 2A. So, if you take a circular orbit like this, how many focus the circular orbit has? It has only one focus. So actually here the focus 1, F1 and F2 both are merged each other as a single point. So, the distance between the two focus F1 and F2 is 0, LC is 0. So, according to the definition, if you substitute LC equals 0, then eccentricity will be equal to 0 for the circle. The same method, we also calculate the eccentricity for parabola and also hyperbola. So, if you go to the parabola, the eccentricity equal to 1 and for hyperbola eccentricity is greater than 1 and for ellipse it is in between 0 and 1, 0 and 1. This is for ellipse. So, these are the curves which has different eccentricity. So, parabola will be like this. So, hyperbola like this, an ellipse like this with the same major axis and minor axis. So this is what eccentricity. So this eccentricity will tell us how much the orbit is deviated from a circular orbit. So here you can see the deviation of the orbits from circular orbit. So here if you see, this is a circular orbit and this is the focus, okay, and eccentricity is 0. And if you see, eccentricity is 0.5, so you can see this is the orbit, the eccentricity 0.5, a small deviation. And if you go to the eccentricity 0.75, you can see the difference is this much from the circular orbit. And if you go for eccentricity 0.9, the deviation is much more. The deviation is much more from the circular orbit. So this is a circular orbit, and this focus is same for all these orbits. And if you go for eccentricity 0.9, so this is the orbit. So as the eccentricity increases, the deviation from the circular orbit increases. Okay, the departure from the circular orbit is increasing. Next, the next topic is inclination of orbit. So it is also one of the very important parameter to understand the orbit and its nature. So coming to the inclination of orbit, if you see here, this is consider this is the Earth, okay, this is Earth, and Earth is rotating in this axis, in this direction, okay, and this red color line, what is the red color line? You can see here, this red color line is the orbit, satellite orbit. And if I draw a plane like this, if I draw a plane along this orbit, okay, which is passing through the Earth equatorial plane, Earth center, then we can call that as orbital plane. Okay, so this orbital plane, and if I take the Earth, this is the Earth, okay, so I will take this is the equatorial plane. If I take this is the equatorial plane which is passing through the equator. So whatever the inclination between these two planes, this plane 1 orbital plane, and this is equatorial plane. So whatever the angle between this orbital plane and the equatorial plane is called orbital inclination. What do we call? The angle between orbital plane and the equatorial plane is called orbital inclination. So if an inclination is 0, suppose if inclination is 0 denotes the orbit is in the equatorial plane. So the object is rotating in the equatorial plane. Okay. Next, the next topic is polar orbit. So what is polar orbit? So a polar orbit is nothing but if the inclination is 90 degrees, then that orbit is called polar orbit. So this inclination 90 degrees is with respect to what? Equatorial plane. Then that is polar orbit. So if you observe here, so here this is the Earth. This is the Earth, and this is the equatorial plane. And this is the plane which is passing through the north and south poles. So this is north pole and this is south pole. You can see this plane is north-south plane. Okay, the plane which is passing through the north and south planes. And if you see, this is a orbit. This is one orbit which is also passing through the north and south poles, which is also passing over the north and south poles. So then this orbit is called polar orbit. So it is passing over the north pole and south pole. So as the Earth rotates about its own axis, this orbit will be stay with some this object is rotating in the polar orbit, so that these whatever the satellites launched in this polar orbit will cover all the parts of the Earth. And generally the satellite which is launched in the polar orbit will go for a revolutions more than 10 revolutions in a day. Okay, so coming to the applications. So as the Earth rotates underneath the satellite's orbit, different areas of the planet can be used in each pass. Whenever for each revolution, the satellite will cover different parts of the Earth. So coming to the applications, for what purpose we use this polar orbits? So generally we use polar orbits for Earth observation. So in order to do Earth observation, we use image satellites, GPS, etc. And next we also use polar orbits for environmental monitoring. So like for scientific satellites, we launch scientific satellites in polar orbits and we observe the changes in environment. Okay, and also we can use weather forecasting. We can use polar orbits for weather forecasting. Here we use weather satellites launch in the polar orbit and observe weather forecasting, right? So to launch a satellite in polar orbit, we use PSLV. PSLV. What is this? Polar Satellite Launch Vehicle. PSLV. Polar Satellite Launch Vehicle to in polar orbit and also in sun synchronous orbit. Even for sun synchronous orbit also we use this launch vehicle PSLV. Next, sun synchronous orbit. So what is sun synchronous orbit? So it is a special type of polar orbit. Okay, sun synchronous orbit is a special type of near polar orbit. Okay, so here what happens is satellite always passes over the same part of the Earth roughly at the same local time. So whatever that like every day the satellite goes in the same position in the sun synchronous orbit, and the satellite's position related to the sun remains constant over the time. So one is the satellite reaches the same position at every day at same time, and also the orbital plane with respect to the sun is maintaining constant. Suppose if I take this is orbital plane. Okay, so this is orbital plane. So this is the Earth, right? So this is Earth and satellite is rotating. Satellite is rotating like this. Okay, satellite is rotating like this. So this is the orbital plane. Okay, and this is the center of the sun and this is the Earth of the sun. So if I join a line like this, this is called sun line, and the angle between this orbital plane and the sun line is sun angle. So whatever throughout the year, whatever the day you take, the angle, this sun angle is constant. This sun angle is constant for a orbital plane. This orbital plane makes equal same angle every day. So for that the orbital plane rotates at 1 degree per day due to the Earth oblateness, and the Earth moves around the sun because Earth also moves around the sun, right, in 360 days. So each day it will precedes by 1 degree per day. Okay, because of this 1 degree per day only, we got the time duration for the sidereal day is 23 hours 56 minutes 4 seconds. So this particular orbit which makes equal same angle with respect to the sun line, and the orbit, the satellite possesses same place in solar time, a particular solar time in a day. That particular orbit is called sun synchronous orbit. So what are the applications of sun synchronous orbit? So sun synchronous orbit, whatever satellite we launch in sun synchronous orbit, that can observe a particular place on the Earth with full sunlight. If you want observe the particular place with full sunlight, every day you can observe that particular place with full sunlight. And if you want to observe a particular place in a dark night, so every day you can observe that particular place at the same time with the same lighting condition. So application. So sun synchronous orbits are commonly used for satellites that needs to capture high quality consistent imagery, okay, such as weather monitoring, environmental observations and GPS mapping. So it will give you a high quality imaging. Sun synchronous orbit will help us to get a high quality images. So this ensure uniform lighting conditions, same lighting condition across different passes over the satellite. Okay, we can observe the particular place with the same lighting condition on every day. So this is especially valuable for applications like agriculture, forestry and climate monitoring. So monitoring the sun and solar activity. Even we can use the satellites by launching in sun synchronous to observe the sun daily. Okay, to observe the sun, to monitor the sun and what are the things, what are the activities that is being happening in the sun can also be observed with the help of sun synchronous satellites. So coming to the India, the satellite which the sun synchronous satellite is Indian remote sensing satellite. We call this as IRS. So IRS series are placed into sun synchronous orbit. All IRS series are placed in sun synchronous orbit SSO. So IRS-1A was the first Indian satellite launched into sun synchronous orbit, and we launched this IRS-1A with the help of Soviet Union. So coming to the summary. So the topics which we have discussed are eccentricity. We have gone through the definition of eccentricity and we have gone through the formula and how this eccentricity affects the shape of a particular orbit, and we have gone through the inclination, we have gone through the polar orbit, we have gone through the sun synchronous orbit and their application. So this is the summary of today's topic: eccentricity, inclination, polar and sun synchronous orbit. In the next class, we will discuss about the energy requirements to reach a particular orbit. Thank you.